Gibson here. Today we're going to look at Newton's second law of motion, which really takes us into the relationship between force and acceleration and actually mass. Let's look at our objectives. So the first is to be able to state the relationship between those three parameters: acceleration, mass, and net force. That relationship is Newton's second law of motion. The second is to solve some simple problems using Newton's second law, and then create a tool that we can use to analyze problems and answer questions like what would be the acceleration, what would be the net force. And these are called free body diagrams. And then third, we're going to look at a special case of Newton's second law of motion applied to an object that is falling through the air, and what effect does the air resistance have on it. All right, so what causes an object to accelerate? Well, if we apply a force to it, but the force is equal, 4 newtons in each direction, we can easily see that those two forces would cancel each other out, and we would no longer have a net force. And if we think back to Newton's first law of motion, the object, if it's at rest, will remain at rest. If it's in motion, it will remain at a constant speed and direction, because there is no net force, or we would call it, we have balanced forces. Now, if we change that to 6 newtons, we no longer have a balanced force, right? We have a net force of 2 newtons to the left, and now the object's motion is going to change, right? If it was at rest, it's going to begin to accelerate. If it was in motion, it could either accelerate to a greater speed or slow it down, depending on the direction of the force and the direction of the motion. So we know an object will accelerate, either speed up or slow down, when there's a net force acting on the object. So let's look at an example. If we apply a 5 Newton force to an elephant, right, we get a certain reaction in terms of the change in its motion. If we apply a 10 Newton force, we double the force. For the same elephant, we would expect to see twice the change in its motion. It's going to accelerate at twice the rate. So what type of relationship do we have between acceleration and net force? Well, if we increase the net force, it increases the acceleration, right? And we call this a direct relationship, right? In that they both change in the same direction. If the net force increases, the acceleration increases. Or the other way is, if the net force decreases, then the acceleration will also decrease. Okay, so we can say that acceleration is directly proportional to the net force. All right, so we know that much. Those two are proportional or directly proportional to each other. Let's look at another case. What is the relationship between mass and acceleration? Well, if we apply the exact same force to an elephant and a mouse, which one's going to accelerate at a higher rate? Well, clearly, the mouse has much less mass, therefore it can be accelerated at a higher rate. The elephant had greater mass, so its acceleration was at a lower rate. So what type of relationship do we have then between mass and acceleration? Well, as we increase the mass, we decrease the acceleration. Okay, if we were to double the mass, we would have half the acceleration. So in this case, right, as mass increases, the acceleration decreases. And we call this an inverse relationship. So we can say acceleration is inversely proportional to the mass. And mathematically, here's how we would write that. Now that little tilde marks or squiggly line there just is another way of saying is proportional to. And in a minute, we'll put it into an equation with an actual equal sign. But 1 over the mass tells us that it's inversely. In other words, as the mass gets larger, right, 1 divided by a larger number gives us a smaller result, a smaller acceleration. All right, let's put it all together. So we have these two relationships between force and acceleration and mass and acceleration. So if we put them together, net force on the top and mass on the bottom, we wind up with this combined relationship. Okay, so what would Isaac Newton say about these two relationships? Well, that's his Newton's second law of motion. So here's what it says. The acceleration produced by a net force on an object is, first, directly proportional to the magnitude of the net force. Okay, so force increases, acceleration increases, and inversely proportional to the mass of the object. As the mass goes up, the acceleration gets smaller or declines. Now, one other important element to Newton's second law is that the acceleration will always be in the same direction as the net force. And this is going to be very important to remember as we solve problems. And I ask you not just for the magnitude of the acceleration, but what direction would the acceleration be in? Okay, so same as net force. So acceleration is in meters per second squared if we use those units, and we use newtons for force and kilograms for mass. We can actually write this as equation. Acceleration equals net force divided by the mass, as long as we have these different units for acceleration, net force, and mass. So here's the equation. It's written right now to solve for acceleration, but we could solve for any one of the three, right? We could solve for mass, net force, or acceleration. So here's two forms of it that we will use most often. A equals F over M if we're solving for acceleration, and F equals ma if we're solving for the force, and we know the mass and the acceleration. All right, let's look at a couple simple examples here. If a single car can accelerate at 2 meters per second, what acceleration can it attain if it is towing another car of equal mass? Okay, so basically we're doubling the mass. So as the mass increases, what's going to happen to the acceleration? Well, we know it's inversely proportional to the mass, so it's going to decrease. How much is it going to decrease by? Well, the mass is changed by a factor of 2. The force is the same, right? The same car and the motor in the car is pulling either itself or both cars. So the acceleration is going to be half. If we double the mass, we'll have half the acceleration. So in this case, the new acceleration would be 1 meter per second squared. All right, let's see if we can just apply the formula here and calculate the acceleration for the first problem and the force for the second. So see if you can go ahead and do this. Pause the presentation. All right, find the acceleration of a 4 kilogram ball if you apply a force of 20 newtons. So this is just what I call a plug and chug, right? We have the force, 20 newtons. We have the mass, 4 kilograms. We just need to plug it into this form of Newton's second law. 20 divided by 4 gives us 5 meters per second squared. Make sure we have the right units for acceleration. Now, not asking for direction in this problem, right? And I don't give you the direction of the force, but they would be in the same direction. All right, the second part, what force now is required to accelerate a 1,000 kilogram car at a rate of 3.5 meters per second squared? So this is the form we're going to use, right? Solving for F. So we just multiply the mass and the acceleration. And in this case, we get 3,500 newtons. All right. An important term here we're going to be using is called equilibrium. And equilibrium is just another word we can use to describe a situation when the net force is 0. In other words, we have balanced forces. We say that the system is in equilibrium. So let's look at this example. We've used it multiple times now. A stack of books on a table. We know it has a weight pushing down on it due to gravitational acceleration, the force on these books. And we also know we have the support or normal force going up that's equal and opposite. So when the weight and the normal force are equal to each other, the net force is 0, and we would say that the system of books with the table is in equilibrium, the state of a body on which no net force acts, or the net force is 0. Now let's talk about this concept of a free body diagram. It's a tool, and we've seen these already a little bit, but we're going to be creating them and using them ourselves today to show the relative magnitude and direction of all forces acting upon an object. It's really a vector diagram. So here's how we do it. The object is represented by a box. So no matter what the object is in the problem, we can just use a box. We don't have to spend a lot of time trying to draw what it actually looks like. The forces are shown as vectors or arrows, and the direction shows what direction the force is acting on the box. So in this example, right, the force is pulling the box downward, or it's pushing the box downward, but probably typically we'd think of pulling down. The length indicates the relative magnitude of the force vector. Okay, so when you draw these, if you know the forces are equal, then draw them about the same length. If you know one is greater than the other, show that. Show it as a longer arrow than the smaller force. The other key thing to remember is that the force vectors are always drawn away from the object. We would not show the vector arrow going into it. And as you look at some examples, you'll see that it's pretty easy to draw that consistently where the arrows are always going away from the object. So in this example, right, we might have a downward force that is due to gravity. So it's good to label each force with a capital F, and then in the subscript, what is the type of force that we're working with. Okay. All right, so let's get a little practice here. What would the free body diagram look like for books resting on this table? Well, let's start with what are the forces? We know we have gravity down and we have normal force up. So we'll draw a box that represents the book. We know these are forces that are equal and opposite to each other. So we're going to draw two vectors, label them, but notice they are in opposite direction, but equal length, equal magnitude. And in this case, right, there would be no acceleration because the net force is zero. These two forces are equal and opposite, and therefore would cancel each other out. All right, let's try another one. It says brakes are applied to a rightward moving car and it skids to a stop. Okay, so let's see if we can identify all the forces. We have gravity acting downward. We have the normal force acting upward. On almost any problem where you have an object resting on a surface, you're going to have these two forces. If it's falling through the air, you're still going to always have the gravitational force. But what other force did we have here? Now we said brakes are applied to a rightward moving car. So if the car is moving to the right but slowing down, the force for the brakes is going to be to the left. And we'll call that a frictional force because it really is the friction between the brake pads and the wheel, or the wheel and the road. All right, let's put it into a free body diagram. Here's our car. We have gravity going down, our normal force going up, and our frictional force to the left. Now, we're not given any information on the magnitude of the frictional force, so we can pretty much draw the arrow any length we want. But the normal and gravitational forces, or arrows, would be good to draw the same length. So there's no net force in the vertical direction, but there is a net force in the horizontal direction to the left. That's what is causing the car to slow down or decelerate. All right, so let's get a little practice here of, if we're given a free body diagram, can we find the net force and then the magnitude and direction of the acceleration? So let's look at this free body diagram. We got a lot of forces here, 4 different forces applied to it. So let's first figure out what is our net force. Now, we'll draw the net force as a single force on our free body diagram. Think of it as a simplified free body diagram. But let's look at what forces we have. Now, the force is up, right? We can treat that as positive. If it's down, we can treat it as negative. So we have a +3 up for the normal and a -3 down for gravity. So those are going to cancel each other out. How about the horizontal forces? Well, we have the same thing. We can treat a force to the right as positive and a force to the left as negative. So we have a +5 applied force, and a -5 frictional force. So those also are going to cancel each other out. So what happened here? All the forces cancel each other out. All we can say here is we have a net force of 0. So this object would be in equilibrium, and therefore the acceleration is going to be 0. Okay? If this object is at rest, it's going to remain at rest. If it's in motion, it's going to remain at a constant speed and direction. All right, let's look at another one here. Same questions. So here, right, the normal force and the gravitational force cancel each other out, just like we saw on the previous problem. But notice we have this frictional force to the left in the horizontal and no other forces to work against it or cancel it out. So here's what our net force would look like, right? We would have 5 newtons and it would be to the left. All right, now let's figure out the acceleration. We know since we have a net force, we will have an acceleration, but we need to know the mass, right? In order to find the acceleration, we have to know the mass. Now, we're not given the mass directly here, but we can find it out. So let's rearrange this equation. If we wanted to solve for the mass, we would need to know the force and the acceleration. Well, there is one force here that we could use to solve for the mass. It's the gravitational force. Okay? So the force we're talking about is the gravitational force. The acceleration is that due to gravity. So notice I replace that with Fg and g. So we can put the values in here, right? We know the gravitational force, it tells us in the free body diagram, is 3 newtons. Acceleration due to gravity, we know that, that's 10. So 3 divided by 10 gives us 0.3 kilograms, right? Remember, we're finding the mass using the gravitational force. Basically, take the gravitational force and divide by 10. So that's what we're going to be doing in each one of these. All right, now that we know the mass, we can use that with the net force, right, of 5 newtons and solve for the acceleration. So 5 divided by 0.3 gives us about 16.7 meters per second squared. Now, what direction would it be? Well, the net force is to the left, so the acceleration will also be to the left. All right, let's do another one here. See if you can work through this one. Okay, so net force in this case is going to be upward, right? 15 newtons, because 40 minus 25 gives us 15. How about the acceleration? Well, let's find the mass first. Take the gravitational force divided by 10. We get 2.5 kilograms. So now we can put that into Newton's law and solve for the acceleration. So 15 divided by 2.5 gives us 6 meters per second squared. What direction would that be? Well, the net force is upward, so the acceleration will be upwards. All right, one more here. Now this one's a little different. Notice we're given the net force of 900 newtons upward. We're being asked to find the missing force C. So here's how we can set it up. Just write the equation to find the net force. So 200 newtons down, notice I put that in as a negative 200 newtons, plus C, our unknown force, has to equal the net force, which is a positive 900, since it says it's up. So now simple algebra, right? If we want to solve for C, we just add 200 to both sides, and we wind up with a net force, the missing force of 1100 newtons. And that will be in the upward direction because we got a positive value for that missing force. All right, let's go ahead and find the magnitude and direction of acceleration. So here, right, we're going to use the 200 newtons that was given us to find the mass. So 200 divided by 10 gives us 20 kilograms. And then we already had the net force to start with, right? So it's just going to be 900 divided by the 20 kilograms, and we get 45 meters per second squared. That's a pretty high rate of acceleration in this case. What direction would it be? Well, the net force is up, so the acceleration will be upwards. All right, last concept about friction here. So friction is a force. It has a magnitude and direction. It acts on materials that are in contact with each other. So it's a contact force, right? We talked about field forces and contact forces. But what actually causes friction? Well, anytime you have two solid objects that come in contact, is due to irregularities between the two surfaces. As hard as we try to create perfectly smooth surfaces, that's really hard to do at a microscopic level. We'll still have little peaks and valleys that are going to have to rub against each other, kind of either grind each other flat or actually lift up and kind of bang over the high points there. So that's what causes friction at a microscopic level. The other key thing about friction is that it always acts in the direction to oppose motion. So if an object is moving to the right but has friction, friction is going to be acting to the left. So friction is in the opposite direction of motion. So that's what this box, if we're trying to move the box to the right, we're having to overcome a frictional force that is to the left, right? So we have to push to the right at least equal to or greater than the friction to cause the box to accelerate or move at least a constant speed to the right. All right, so friction can be more than just between two solids, right? We have something called drag, and that is the frictional force through a fluid, and the fluid can be either a gas or a liquid. Air resistance is the drag on a force when it moves through the air in our atmosphere. And the magnitude of it depends actually on a lot of things. It's very complex to determine what the air resistance of an object would be, but it depends on the object's speed, right? If it's not moving, if it's at rest, it has no air resistance. But once it begins to move, it develops air resistance. Its shape and the density of the fluid or the air. So the shape makes sense, right? If you think of when you hold your hand out the car window when you're driving, if you keep your hand flat, right, you feel a little bit of resistance, but you turn your hand sideways and you feel a lot of air resistance or pressure force being pushed on your hand here. So here's some shapes, right? We have a ball, we have an airfoil like a wing, we have just a block of air that would be kind of like your hand. They all will have different amounts of air resistance. The square block would have the greatest, the wing would have the least amount of drag or air resistance. Now it's interesting that if you watch the speed skaters in the Olympics, it turns out about 30% is the drag of their skates on the ice. They're actually very low resistance, and most of the drag they have to overcome is the air resistance, and that's why you see them wearing those really smooth, tight suits so that they can minimize the air resistance as they're traveling. Here's another example. We have a jet airplane flying through the air. There are jet engines. If they created 50,000 newtons of thrust, that's the term for the force that's created by the jet engine. If they're traveling at a constant velocity, that means the air drag or air resistance would be equal and opposite, 50,000 newtons in the other direction. So a jet airplane has to create at least enough thrust, right, to overcome the drag or air resistance as it travels through the air, even if it's climbed up to its altitude and is flying at a constant velocity. All right, we're going to look at a special case here, and we'll do some more work with this later this week. But how does falling through the air and air resistance react with each other? So when a skydiver jumps out of an airplane, what kind of acceleration do they experience? Well, the minute they release themselves, right, they don't have any velocity, so they wouldn't have any air resistance, and they would begin to accelerate at 10 meters per second squared. But as they begin to pick up speed, their air resistance will begin to increase, okay? So we have gravitational force pulling them down. That will be constant, but the air resistance will become greater and greater as they go faster and faster. It also depends on their shape, right? You see skydivers that will tuck into a ball and can fall faster. If they spread their arms and legs out wide, they can slow themselves down. So we call this terminal velocity. At some point, the gravitational force and the force due to air resistance upwards are equal to each other. And when that occurs, we have what we call terminal velocity. Let's watch a short video here.
Remember Galileo's problematic experiment when he proved that two different weights would hit the ground in a dead heat when dropped from the Leaning Tower of Pisa? It stirred up a hornet's nest back then, but now we know he was right. Gravity rules. And that brings us to terminal velocity of humans. We're talking about the gravitational effect on someone who's jumped out of a plane and accelerates to a top speed before they open their chute. But what is their maximum speed? Is it 200 miles per hour, 150 miles per hour, or 125 miles per hour? The answer is 125 miles an hour. Falling things will accelerate downwards, but, and it's a big but, you don't keep accelerating because of one thing, the opposing force of friction with the air. So, when the opposing force of friction equals the downward force of gravity, you stop accelerating and fall at the rate known as terminal velocity. There is another way. It was perfected by a man named Joseph Kittinger in 1960. He dove out of a balloon 102,000 feet up and got to 614 miles an hour. Mind you, that was in thin air before frictional forces could slow him down. But still, 614 miles an hour? That's almost the speed of sound. That would give you a head rush.
So besides skydivers with parachutes, they often have these wingsuits, and they can change their shape and their orientation to be able to either increase or decrease their terminal velocity and actually create some lift and, in essence, almost fly through the air. I'm going to post a video with this assignment that you can watch that shows some pretty amazing skydivers here using their wingsuits. So check that out. All right, so that's it for the lesson. We know how to state the relationship between acceleration, mass, and net force, and explain that as Newton's second law of motion. We've solved some simple problems and then looked at the effects of friction, particularly the case of air resistance on a falling object.